Contextual effects of angry vocal expressions on the encoding and recognition of emotional faces. An event related potential study. Lin and Liang. Abstract. It has been shown that stimulus memory, for example, encoding and recognition, is influenced by emotion. In terms of face memory, event related potential studies have shown that the encoding of emotional faces is influenced by the emotion of the concomitant context when contextual stimuli were input from a visual modality. Behavioral studies also investigated the effect of contextual emotion on subsequent recognition of neutral faces. However, there might be no studies ever investigating the context effect on face encoding and recognition when contextual stimuli were input from other sensory modalities. For example, auditory modality. Additionally, it may be unknown about the neural mechanisms underlying context effects on recognition of emotional faces. Therefore, the present study aimed to use vocal expressions as contexts to investigate whether contextual emotion influences ERP responses during face encoding and recognition. To this end, participants in the present study were asked to memorize angry and neutral faces. The faces were presented concomitant with either angry or neutral vocal expressions. Subsequently, participants were asked to perform an all new recognition task in which only faces were presented. In the encoding phase, ERP results showed that compared to neutral vocal expressions, angry vocal expressions led to a smaller P1 and N170 responses to both angry and neutral faces. For angry faces, however, late positive potential LPP responses were increased in the angry voice condition. In the later recognition phase, N170 responses were larger for neutral encoded faces that had been presented with angry compared to neutral vocal expressions. Preceding angry vocal expression increased FN400 and LPP responses to both neutral encoded and angry encoded faces when the faces showed the encoded expression. Therefore, the present study indicates that contextual emotion with regard to vocal expression influences neural responses during face encoding and subsequent recognition. Introduction. It has been demonstrated that emotion influences memory formation. In the case of face memory, research has shown that face memories, such as face encoding and recognition, is increased by emotional expression of the face. For example, angry and fearful expression, when the face is presented in isolation, that is, they are not presented with other stimuli. In everyday life, however, there are many circumstances that faces are not viewed in isolation, but in the context of other emotional stimuli, such as concomitant contextual scenes, body, and vocal expressions. In this case, the emotion is not only elicited by the facial expressions, but also by other factors such as those contextual scenes, body, and vocal expressions. The question of interest would be how the encoding and recognition of emotional faces are influenced by the emotion of these contextual stimuli. Regarding face encoding, ERP, event related potential studies, have identified several indexes to reflect effects of contextual emotion. The P1, for instance, is a positive component that starts approximately 100 milliseconds after stimulus onset over occipital scalp sites. This component is thought to be associated with perceptual encoding of a face. In a subsequent time range, the N170, a face sensitive component that peaks around 170 milliseconds after stimulus onset and is maximal over posterior scalp sites, is supposed to reflect structural encoding of a face. In the later time ranges, the P3, or late positive potentials, LPP, starts around 300 milliseconds with the onset of stimulus and is widely distributed over central and parietal scalp sites. This component is thought to be related to complex and cognitive encoding. Using these indexes, several studies have utilized visual stimuli, for example, scenes and body expressions, as context to investigate the effects of contextual emotion on the encoding of emotional faces. As far as the P1 is concerned, Rigert and the Gelder 2006 found that P1 responses were slightly larger for both fearful and neutral faces when they were overlapped onto negative scenes compared to neutral scenes. Gu et al. 2013 also showed larger P1 responses to both fearful and happy faces that were presented with fearful compared to happy body expressions. Regarding the N170, emotional faces were found to evoke larger N170 responses when the faces were paired with negative compared to positive and neutral scenes. With, with respect to the P3/LPP, LPP responses were larger for fearful faces within negative as compared to positive scenes, and for happy faces within positive as compared to negative scenes. The P3 response was also found to be larger for fearful faces that were presented together with fearful compared to happy body expressions, and for happy faces that were presented with happy compared to fearful body expressions. Taken together, the findings may indicate that perceptual and structural encoding of emotional phases are associated with specific emotion of the context, negative emotion in particular. The cognitive encoding of the faces is suggestive to be related to emotional congruency, that is, emotion integration between contexts and faces. With respect to face recognition, two behavioral studies investigated the effect of contextual emotion on subsequent recognition of neutral faces. In this study by von den Stock and de Gelder 2012, recognition of neutral faces was found to be impaired when they had been encoded with negative and positive compared to neutral scenes and body expressions. In Purgitty and colleagues study 2016, however, the authors did not find an effect of contextual emotion on subsequent recognition of faces. A possible reason for the discrepancies may be related to exposure duration, face encoding, and recognition. For example, 1000 milliseconds in Van der Stock and de Gelder's 2012 study and 3000 milliseconds in Purgitty and colleagues' 2016 study. Long exposure duration may increase stimulus retrieval in general, and thus reduce the effect of contextual emotion on face recognition. Taken together, the above mentioned studies indicate that contextual emotion influences face encoding and recognition when contextual stimuli are input from a visual modality. In the real world, emotional faces are often encountered as accompanied by context of other sensory stimuli, for example, auditory stimuli. For instance, after making a mistake, you may see the angry face from your father while you are listening to your mother scolding you. However, few studies have investigated the effect of contextual emotion on face encoding and recognition when the context is used by auditory stimuli. Regarding face recognition, previous studies have investigated the effect of contextual emotion only when faces are presented in a neutral expression. As is suggested in the above mentioned paragraphs, face encoding, particularly associated with the LPP, is influenced not only by contextual emotion but also by facial expression. For example, emotional congruency between contextual and facial emotions. Encoding, which is the first step of memory, is thought to affect later stages such as recognition. Therefore, effects of contextual emotion on face recognition may be also influenced by facial expression. Moreover, the research about neutral correlates underlying the effect of contextual emotion on subsequent face recognition is sparse. Previous ERP studies have suggested effects of contextual emotion on face encoding at different stages of processing. As mentioned above, the processing of face encoding might influence face perception in a later recognition phase. Thus, preceding contextual emotion might also influence neural responses in different stages of face recognition. The investigation of this issue may gain a better understanding of long term effects of contextual emotion on face memory. Taken together, the present study aimed to investigate whether contextual emotion with respect to vocal expression influenced ERP responses during encoding and recognition of emotional faces. To address this issue, participants in the present study were presented with angry and neutral faces. The faces were paired with either an angry or a neutral vocal expression. Participants were asked to learn the faces regardless of facial and vocal expressions. Subsequently, the encoded faces and some new faces were presented without any vocal expressions. Considering that the effect of contextual emotion on face recognition may be different when faces show the encoded or a new expression, the faces would be presented with either the encoded expression or a new expression during recognition phase. Participants were asked to identify whether the prompted faces had been presented before, regardless of facial expression. Electroencephalograms, EEGs, were recorded for both encoding and recognition phases. Regarding face encoding, previous studies using visually contextual stimuli showed that contextual emotion influenced P1, N170, and LPP responses during face encoding. Therefore, in the present study, we predict that the effect of vocal expression on face encoding would be shown in P1, N170, and LPP responses. Regarding P1 and N170, these components have been suggestive to be associated with negative emotion of the context. When emotional faces were presented with visually presented context, it was found that negative compared to neutral context increased P1 and N170 responses to emotional faces. In these studies, however, faces were presented to be overlapped onto pictorial context or to be close to the context of body expression. Due to close proximity in space, attending to contextual stimuli would also attend to the faces. That is, when contextual stimuli were encoded, the faces would be also encoded. Given that the encoding is thought to be better for negative compared to neutral stimuli, negative compared to neutral context in previous studies should also have better encoding, thus resulting in an increased perceptual and structural encoding of faces reflected by P1 and N170, respectively. However, in the present study, faces and contextual stimuli, voices, are from different modalities, and thus they are not close in space. Attending to voices would not increase the attention towards the faces. Therefore, the P1 and N170 effects of vocal context might be different from the effects regarding visual context. With respect to the P1, Gerdes et al. 2013 showed reduced P1 responses to unpleasant pictures within unpleasant compared to pleasant sounds. In this study, the onset time of sounds was slightly earlier than that of pictures. However, presenting auditory stimuli prior to visual stimuli seemed to be unrelated to the emotional P1 effects of auditory stimuli on visual stimuli. And thus, the P1 effect shown by Gerdes and colleagues' 2013 study should be not associated with presentation pattern. In terms of the N170, no studies, to the best of our knowledge, have found the emotional N170 effects of auditory stimuli on faces processing. However, it has been shown that task-irrelevant voices interfere with the encoding of visually presented items. Such interference effects could be shown at least in posterior N1, which is thought to overlap with the N170 in face studies, with reduced posterior N1 responses to visually presented stimuli paired with voices compared to without any sounds. Moreover, due to emotional salience, the processing of negative auditory stimuli is more attentive and thus more automatic than the processing of neutral auditory stimuli. This increased automatic processing may enlarge the interference on the encoding of visual stimuli and thus reduce posterior N1 responses. Taken together, We predict that P1 and N170 responses would be smaller for faces that are presented with an angry compared to neutral vocal expression. Different from automatic stages of processing, for example, P1 and N170, at controlled stages, for example, LPP, individuals can distribute attentional resources in a controlled way. In order to reduce the interference effects at early automatic stages, participants may pay large attentional resources to encode the faces at controlled stages. This issue may particularly occur in the angry voice condition, as at early stages, angry compared to neutral vocal expression produce stronger interference effects on face encoding. Additionally, in LPP time ranges, the brain may integrate emotional expressions of different stimuli. This integration may boost the anger elicited by vocal expression to emotionally consistent faces and thus increase the encoding of relevant faces. Taken together, we predict that angry compared to neutral vocal expression would enhance LPP responses to faces, angry faces in particular. Regarding face recognition, there is evidence indicating that context presented with a target stimuli in the encoding phase influences several ERP components, for example, N170, FN400, and LPP, and later recognition of target stimuli. For the N170, Morgan et al. 2008 found that recognition of faces produced smaller N170 responses when these faces had been encoded with distractors than without. This finding may imply that previous interference effects can be further processed in N170 time ranges during face recognition. In the present study, perceptual and structural encoding of faces are impaired by angry vocal expression at early time ranges of processing, for example, P1 and N170, whereas at later time ranges, for example, LPP, cognitive encoding is more elaborate for faces within angry vocal expression. Considering that LPP time ranges are much longer than P1 and N170 time ranges, after the encoding phase, faces may generally have less interference and have more elaborate encoding in the angry face condition than in the neutral voice condition. Therefore, we predict that preceding angry vocal expression would increase N170 responses during face recognition. According to dual process models, performance on recognition tests can reflect the assessment of stimulus, familiarity, and recollection of details about a previous episode. Familiarity is thought to be associated with a continuous content free assessment of memory strength, whereas recollection involves the ability to retrieve specific details associated with the original experience. In ERP studies, familiarity has been found to be associated with FN400, a component starting around 400 milliseconds after stimulus onset and being distributed over frontal scalp sites. While recollection has been thought to be reflected by recognition related LPP, a component that is similar to the encoding related LPP in time ranges and scalp distribution. More importantly, regarding effects of contextual emotion, Ventura Board and colleagues in press reported that when participants were asked to memorize objects that were presented with either task relevant emotional and neutral pictures, and later to recognize these objects, results show that recognition of the objects elicited smaller FN400 and larger recognition related LPP responses in the emotional condition than in the neutral condition, suggesting that objects are more familiarized and have stronger recollection when they have been encoded with task irrelevant emotional compared to neutral contextual stimuli. Accordingly, we predict that face recognition would produce smaller FN400 but larger LPP responses in the angry voice condition than in the neutral voice condition. In addition, the present study also investigated the O new effects to be in line with previous ERP studies. The O new, the O new effects in ERP studies refers to the comparison of ERPs elicited by stimuli correctly judged as old, that is hits, and ERPs elicited by stimuli correctly judged as new, that is correct rejections. It has repeatedly been shown that, compared to those new stimuli, the old stimuli produced smaller FN400 but larger LPP responses. These two effects are in line with the above mentioned dual process models, in which recognition decisions are based on familiarity and recollection. However, studies regarding emotion did not always show that the ONU effects, the FN400 effects in particular. For example, there was a study showing that the ONU effects were reduced for low and extremely high negative stimuli, possibly due to the inhibition of memory function for these two stimuli. Winterbort and colleagues show that ONU effects were shown for learned objects when they had been presented with tasky relevant emotional contextual pictures. However, no new effects were found when the learned objects had been presented with neutral pictures, possibly due to reduced motivational values for the objects within neutral context. In the present study, angry vocal expression boosts the anger of emotionally consistent faces and thus may increase negative evaluation of relevant faces. Neutral faces may be evaluated as slightly negative when they are encoded with angry vocal expression, that is, in the angry voice condition. Faces are evaluated as either very high or low negative. For the other half of the faces, they are presented in task irrelevant neutral vocal expressions. Considering the above mentioned studies, it is still uncertain whether there would be any old new effects, the FN400 effect in particular, in the present study. In addition, given that seldom studies report old new effects in P1 and N170, we would not predict the old new effects would be shown in the P1 and N170. Methods. Participants. 26 undergraduate students were recruited as participants in return for course credit. 3 was excluded from the statistical analysis due to an insufficient number of artifact-free EEG trials and less than 15, resulting in a total of 23 participants, 9 females. All participants were right-handed as assessed through the Edinburgh Handness Inventory. Participants reported normal or corrected to normal vision and no history of neurological illness. All participants have given informed consent in accordance with standard ethical guidelines as defined in the Declaration of Helsinki. The study was approved by the Academic Committee of School of Public Administration, Guangdong University of Finance. Stimuli. Vocal expression. The voices were obtained from the database of the Montreal Effective Voices. This database consisted of 70 short and non-linguistic interjections. The vowel ah, expressing basic emotions, that is, anger, disgust, fear, happiness, sadness, and surprise. And a neutral expression portrayed by 10 different actors. Among this database, the present study selected 20 short interjections portrayed by 5 females and 5 male actors, with angry and neutral prosodies for each. The presentation of voices was edited into meaningful segments of 2.5 seconds, similar to the presentation of faces. The stimuli were recorded and digitized through an audio interface with 44.1 kilohertz sample rates and 16-bit resolution and were normalized peak value 90% of maximum amplitude. In the encoding phase, each vocal stimulus was presented 10 times, half in the neutral phase condition and half in the angry phase condition. Facial, facial expression. The face stimuli were selected from CASPEAL, large-scale Chinese face database, and Chinese Academy of Sciences Institute of Automation, CASIA 3D Face V1. The present study included 600 facial pictures that portrayed 300 identities, 150 male and 150 females, with an angry expression and neutral expression for each. Facial pictures were cropped similarly around the face outline and centered so that eyes, noses, and mouths were located at similar positions. Outer parts of the neck and shoulders were removed. facial pictures were adjusted to a size of 6.75 centimeters to 6 to 9 centimeters, horizontal versus vertical, and were converted to grayscale using Adobe Photoshop CS6. The pictures were also aligned in luminance, contrast, hue, and color using Adobe Photoshop. Finally, the background color was set to black. As is shown in Figure 1, facial pictures were distributed randomly into 5 parts according to facial identity, with 120 facial pictures, 30 females and 30 males, 60 angry and 60 neutral, for each. In each part, 40 facial pictures, 10 males, 10 females, 20 angry, 20 neutral, serve as novel facial pictures to be presented during the recognition phase. The remaining 80 facial pictures, 20 females and 20 males, 40 angry and 40 neutral, were used as target facial pictures. These target facial pictures were separated into 4 sets pseudo randomly with 10 identities for each: 5 females and 5 males, 10 angry and 10 neutral. Each set was divided into 2 subsets, 10 identities each, according to facial expression. Half of the subsets with different identities were presented in both encoding and recognition phases, and the other half of the subsets were presented only in the recognition phase. These 5 parts of facial pictures would be distributed randomly for 5 blocks in the actual experiment, with 1 part of facial pictures for each block. Each block included an encoding phase and a recognition phase. In the encoding phase, half of the subsets, that is, 2 subsets of angry target pictures and 2 subsets of neutral target pictures with different identities, were used to create 4 experimental conditions for the encoding phase: angry, voice angry, face, angry, neutral, neutral, angry, and neutral, neutral. Assignment of subsets was counterbalanced across participants. In the recognition phase, all subsets of target facial pictures were presented to have 2 conditions for learned faces: changed and unchanged, regarding the expression. That is, there were 8 experimental conditions for this phase. That is, unchanged angry voice, angry face, unchanged angry neutral, unchanged neutral angry, unchanged neutral neutral, changed angry angry, changed angry neutral, changed neutral angry, and changed neutral neutral. Novel identities in the recognition phase were also presented with 2 expressions, that is, angry novel and neutral novel. In each block, each target facial picture was presented once in the encoding phase. For the recognition phase, all target facial pictures, including changed and unchanged expressions and novel facial pictures, were presented once. A face showed in a block would not be shown in other blocks. Therefore, for each block, there were 10 target facial pictures for each experimental condition, 4 conditions. In the encoding phase, and 10 target faces for each experimental condition, 8 conditions, 20 angry novel faces, and 20 neutral novel faces in the recognition phase. That is, the experiment consisted of 200 trials, 10 trials per condition per block times 4 conditions times 5 blocks in the encoding phase, and 600 trials, learned faces, 10 trials per condition per block times 8 conditions times 5 blocks plus novel faces, 20 plus 20 trials per block times 5 blocks in the recognition phase, in a total of 800 trials. Procedure: after informed consent had been given and handedness had been determined, participants were asked to sit in a comfortable chair in a quiet room approximately 80 centimeters directly in front of a 23-inch computer screen. Screen resolution 640 to 480 pixels. Participants were asked to avoid moving their eyes and bodies during the presentation of the stimuli. The stimulus presentation was controlled and behavioral responses were recorded by E prime 2.0 software. All stimuli were presented against a dark background. As is illustrated in Figure 1, the actual experiment consisted of 5 blocks. In each block, there was an encoding task and a subsequent recognition task. Each block started with the encoding task. After all the target faces had been encoded in the encoding task, the recognition task began. Before each encoding recognition task for each block, participants were presented with an instruction sheet to remind them about the task demand. There was a break between blocks. The duration of the break was controlled by the participants. The next block started immediately after the break. The complete experiment with the encoding and the recognition phase, including the preparations, lasted approximately 2 hours. For the encoding task, each trial started with a white fixation cross for 300 milliseconds, followed by a blank screen ranging from 1000 to 1400 milliseconds. Subsequently, a face was presented concomitant with a piece of gender consistent voice for 2500 milliseconds. Participants were asked to memorize the face regardless of vocal and facial expressions. Presentation sequences of facial stimuli were randomized across participants. The next trial started after another blank screen for 700 milliseconds. The recognition task immediately followed the encoding task. For this recognition task, each trial started with a white fixation cross that were presented for 300 milliseconds, following in a blank screen ranging from 1000 to 1400 milliseconds. A face was presented for 2500 milliseconds. Notably, the faces were presented in isolation without any vocal expression. Presentation sequences of facial stimuli were randomized across participants. Participants were asked to identify whether the identity of the prompted face had been shown in the preceding encoding phase or not. By pressing the keys F and J using the index finger of the left and right hands, respectively, during the presentation of faces. It was particularly emphasized the judgment was based on facial identity, irrespectively of facial expression. For example, previously, identity A showed an angry expression. In the following task, A will show an angry or a neutral expression. Both angry and neutral, A should be judged as old. The instructions also emphasized speed and accuracy. Response assignments were counterbalanced across participants. The subsequent trial started after another blank screen for 700 milliseconds. Behavior recordings, hit and false alarm rates, as well as response times of button presses, were recorded in the recognition phase. For the analysis of response times, trials only with correct responses were included. EEG recordings. Continuous EEGs were recorded using two 32 brain amp amplifiers. The 33 AG/AGCL electrodes were placed on the scalp by means of an easy cap electrode system, according to the 10% system. The electrode AFZ was used as the ground electrode. All other channels were referenced to the electrode FCZ during data collection. The horizontal oscillogram EOG was recorded from two electrodes at the alta canthi of both eyes, and the vertical EOG was recorded bipolarly from two electrodes above and below the right eye to monitor eye blinks and movement. All signals were digitized with a sample rate of 1000 Hz. Bandpass filtering of 0.016 to 100 Hz was applied with a 50 Hz notch filter online. Impedance were below 10 kilo ohms. EEG data were further processed offline using Brain Vision Analyzer 2.0 software. Muscle and movement artifacts were identified using semi automatic raw data inspection. Ocular movements were inspected and removed from the EEG signal using the algorithm by Gratum et al. 1983. After ocular correction, data were visually inspected to detect whether there were any remaining artifacts, for example, flat lines. The continuous EEG was then segmented from minus 200 to 800 milliseconds relative to phase onset in both encoding and recognition phases, with the first 200 milliseconds a epoch for baseline correction. Notably, previous studies showed differential neuroactivity for stimuli that can be recognized compared to those that cannot. And many ERP studies only analyzed the stimuli that had been recognized correctly. Therefore, the recognition phase in the present study analyzed the phases only for correct responses. Artifact rejection was performed with the amplitude threshold of 100 microvolts. Artifact free trials were analyzed for each channel and experimental condition. Average ERPs were then low pass filtered at 30 Hz and recomputed to average reference, excluding vertical and horizontal EOG channels. The minimum number of trials for a participant in any experimental condition was 15, ranging from 22 to 50 in the encoding phase and ranging from 15 to 44 and for 30 to 82 for learned and novel trials in the recognition phase, respectively. ERPs were quantified using the amplitudes of P1 and 170 and LPP for both encoding and recognition phases, and FN400 in the recognition phase based on visual inspection and previous study. The P1 was measured at the electrodes O1, OZ, and O2, the N170 at the electrodes P7 and P8, the LPP at the electrodes CZ, CPZ, and PZ, and the FN400 at the electrode FZ and FCZ. Regarding the time window, the P1 and LPP were measured at 115 to 145 milliseconds and 500 to 800 milliseconds, respectively, for both encoding and recognition phases. And the FN400 was measured at 350 and 500 milliseconds for the recognition phase. For the N170, however, as is shown in figures 2, 4, 5, and 8, the encoded related N170 has a gentler peak and longer peak latency compared to the recognition related N170, particularly in the left hemisphere. Therefore, we would use different time windows for encoding and recognition related N170, that is, 170 to 210 milliseconds and 160 to 200 milliseconds, respectively. Data analysis. For behavioral responses, response accuracy was used to calculate the sensitivity index, D line. The D line values were submitted to a 2 by 2 by 2 repeated measures analysis of variance, ANOVA, with consistency, changed versus unchanged, vocal expression, angry versus neutral, and encoded facial expression, angry versus neutral, as within subject factors. This ANOVA was also performed on response times for learned faces. The mean and standard error were shown in Table 1. With regard to ERP data, we averaged the amplitude of P1, N170, and LPP for all electrodes of interest. The encoding ERPs, that is, P1, N170, and LPP, were separately performed a 2 by 2 repeated measures ANOVA with vocal expression, angry versus neutral, and facial expression, angry versus neutral, as within subject factors. Grand average waveforms of the components and topography maps for the encoding phase are shown in figures 2 to 3. For the recognition ERPs, the above mentioned 2 by 2 by 2 ANOVA was performed separately on the amplitudes of P1, N170, FN400, and LPP. Grand average waveforms of the amplitude for the recognition phase and topography maps are shown in figures 4 to 7. In order to understand the old new effects, we also performed the repeated measures 2 by 2 ANOVA with novelty, learned versus novel, and facial expression in the recognition phase, angry versus neutral, as within subject factors separately on the amplitudes of P1 and 170, FN400, and LPP. Grand average waveforms of the amplitudes for these effects and topography maps are shown in figures 8 and 9. Statistical analysis were performed using IBM SPSS statistical software. Greenhouse Geyser correction were applied to correct degrees of freedom, and p-values were where appropriate. Bonferroni corrections were used to correct post hoc t-tests. Results. Behavior results. Hit rates were assessed by sensitivity index, that is, D-line. The analysis on D-line values showed main effects of consistency and encoded facial expression. The D-line value was generally larger in the unchanged condition than in the changed condition, and for angry encoded faces compared to neutral encoded faces. Other main effects or interactions did not reach statistical significance. The ANOVA on response time showed only a main effect of consistency, with shorter response times in the unchanged condition than the changed condition. No any other main effects or interactions were significant. For descriptive data, please refer to Table 1. ERP results in the encoding phase. P1. The analysis on P1 amplitude showed only a main effect of vocal expression. The amplitudes were generally larger for faces that were presented together with neutral compared to angry vocal expressions. No any other main effect or interaction was significant. N170. The analysis showed only a main effect of vocal expression. The 170 amplitudes were more negative for faces that were paired with neutral compared to angry expressions. No any other main effects or interactions were significant. LPP. The ANOVA on LPP amplitude showed a main effect of vocal expression rather than facial expression. Post hoc t-tests showed that LPP amplitude was generally larger for faces that were presented with angry compared to neutral vocal expressions. The main effect was further quantified by a trend for the interaction between vocal expression and facial expression. Further analysis showed that there was an effect of vocal expression for angry faces. The amplitude of LPP was larger for angry faces presented with angry compared to neutral vocal expressions. However, the effect of vocal expression was not significant for neutral faces. ERP results in the recognition phase. Effects of consistency, vocal expression, and encoded facial expression. P1. The analysis of the recognition related P1 showed main effects of encoded facial expression. The P1 amplitudes were generally larger for angry encoded compared to neutral encoded faces. No other main effects or interactions were significant. N170. The analysis of the N170 only showed a two-way interaction between encoded facial expression and vocal expression. Further analysis showed that neutral encoded faces evoked larger N170 amplitudes when they had been presented with angry compared to neutral vocal expressions, whereas this effect was not shown for angry encoded faces. There were no any other main effects or interactions were significant. FN400. The ANOVA showed a trend for the main effect of vocal expression. The main effect was further quantified by a two-way interaction between consistency and vocal expression. Further analysis showed that in the unchanged condition, the FN400 was more negative for faces that had been encoded with neutral compared to angry vocal expressions, whereas the effect of vocal expression was not significant in the changed condition. No other main effects or interactions were significant. LPP. The analysis showed only an interaction between consistency and vocal expression was significant. Further analysis did not show any effects of vocal expression in either the changed or unchanged condition. However, as is shown in figures 6 and 7, there's a clear interaction at the electrode CZ with the effect of vocal expression in the unchanged condition rather than the changed condition. Therefore, we tried to analyze the interaction between consistency and vocal expression only at the electrode CZ. Indeed, the results showed an interaction between consistency and vocal expression in the CZ. Further analysis showed that the LPP amplitudes were larger for faces that had been presented together with angry compared to neutral vocal expressions in the unchanged condition, whereas the effect of vocal expression was not significant in the changed condition. There were no other significant main effects or interactions. Effects of old, new, and facial expression in the recognition phase. P1. No main effects or interaction was significant. N170. The analysis did not show any main effects or interactions. FN400. The analysis did not show any main effects or interactions. LPP. The analysis on the LPP showed no new effect. In general, the LPP amplitudes were larger for learned compared to novel faces. Other main effect or interaction was not significant. Discussion. The present study investigated whether contextual emotion with regard to vocal expression influenced ERP responses during face encoding and subsequent recognition. In line with the hypothesis, the results showed that in the encoding phase, both angry and neutral faces produce smaller P1 and N170 responses when they were presented together with angry compared to neutral vocal expressions. For angry faces, LPP responses were larger within angry compared to neutral vocal expressions. In a later recognition phase, while the results did not show an effect of vocal expression in the P1, the effect was evident in the N170, FN400, and LPP. The N170 responses were larger for neutral encoded faces that had been presented with angry compared to neutral vocal expressions. Faces elicited smaller FN400 but larger LPP responses when they had been encountered with angry compared to neutral vocal expressions. And this effect generated not only for neutral encoded faces, but also for angry encoded faces, especially when the faces showed the encoded expression in the recognition phase. Taken together, the findings generally indicate that contextual emotion with regard to vocal expression modulates neural responses during encoding and recognition of emotional faces. However, behavioral results, D-line or response times, did not show any effects of vocal expression. Contextual effects of vocal expression on face encoding. As mentioned in the introduction section, the P1 and N170 are related to perceptual and structural encoding of faces, respectively. In later stages of processing, the LPP is supposed to reflect complex and cognitive encoding. Therefore, the findings in the present study indicate that angry compared to neutral vocal expressions have a stronger interference on perceptual and structural encoding of emotional faces. However, cognitive encoding of angry faces is more elaborate in the angry voice condition than in the neutral voice condition. The object oriented episodic record OOER model proposes that for auditory stimuli, brains encode the objects of the stimuli and serial order information of these objects automatically. However, the encoding of visual presented items is not automatic but requires attention. This automatic encoding of auditory rather than visual stimuli may interfere with the encoding of visually presented items. According to the OOER model, vocal expression in the present study may interfere with the encoding of faces. The interference effect of vocal expression on face encoding may occur particularly at automatic time ranges of face processing, for example, P1 and N170, as in these time ranges, individuals cannot concentrate on the encoding of task relevant faces and inhibit the processing of task irrelevant voices in a controlled way. More importantly, the negativity bias theory suggests that, due to biologically and evolutionary salience and high motivational values, individuals have an attentional bias of negative stimuli. The studies by Latinas et al. 2010 show that attending to voices reduced perceptual and structural encoding of faces reflected in the P1 and N170 when faces were presented with voices. Therefore, in the present study, participants may have a stronger attentional bias of angry compared to neutral vocal expression, and thus reduce perceptual and structural encoding of faces reflected in the P1 and N170, respectively, to a larger extent. Notably, the interference effect, at least in the P1, of emotional, auditory stimuli on the encoding of visual stimuli might occur even though both visual and auditory stimuli are task relevant. For instance, Gerdes and colleagues' 2013 study showed reduced P1 responses to unpleasant pictures within unpleasant compared to pleasant sounds. When the task was to rate on valence and arousal elicited by the combination of both pictures and sounds. This may be because the automatic encoding of task relevant auditory stimuli also interferes with the encoding of visual stimuli, particularly when auditory and visual information are not integrated with each other. For example, P1 time ranges. Therefore, similar to task irrelevant auditory stimuli, the encoding of task relevant negative compared to non negative auditory stimuli have stronger interference on the encoding of visual stimuli reflected in the P1 to a larger extent. However, as no studies, to the best of our knowledge, have ever investigated the emotional N170 effects of task relevant auditory stimuli on face processing, whether the N170 effects are dependent on task demands, for example, either visual stimuli or both visual and auditory stimuli were task relevant, should remain to be investigated in future studies. Different from early time ranges, for example, P1 and N170, at later time ranges, for example, LPP, individuals were able to allocate attentional resources in a controlled way. Therefore, in the present study, participants may take the initiative to pay large attentional resources to have an elaborate encoding of faces. Moreover, this issue may particularly occur for the faces with an angry vocal expression, as the encoding of these faces had been strongly impaired by preceding P1 and N170 time ranges. Therefore, the findings in the present study showed increased encoding of angry faces reflected in the LPP in the angry voice condition. Additionally, in the LPP time ranges, brains may integrate emotional information for different stimuli. This integration may boost the anger from vocal expression to emotionally consistent faces, thus resulting in more elaborate encoding of relevant faces. However, the effect of vocal expression on LPP responses was not observed for neutral faces. Different from negative stimuli, neutral stimuli is not biologically important. Integrating neutral emotion between facial and vocal expressions may be not much help in increasing cognitive encoding of neutral faces. In the angry voice condition, however, neutral faces may be encoded very elaborately in order to reduce the impairment effects in preceding time ranges. The failure of the effect of vocal expression may be due to increased cognitive encoding in the angry voice condition. Different from the findings in the present study, previous studies using visually contextual stimuli, for example, scenes and body expressions, show larger P1 and N170 responses to emotional faces that were presented together with negative compared to neutral context. However, in line with the findings in the present study, related studies show that P3 slash LPP responses were larger for fearful faces within emotionally consistent context. The inconsistent P1 and N170 effects and consistent LPP effects between the previous studies and the present study may be associated with stages of face processing and spatial proximity between contexts and faces. At early stages, the face processing, for example, P1 and N170, individuals cannot allocate attentional resources to encode the faces in a controlled way. The quality of face encoded depends on how much attention the face themselves can capture. In previous studies, faces were presented either to be overlapped onto the center of visually contextual stimuli or to be close to the stimuli. Due to spatially close proximity between faces and context, attending to contextual pictures and bodies also attended to simultaneously presented faces. Given that negative compared to neutral stimuli can capture more attention, in previous studies, target faces close to negative context could capture more attention than faces close to neutral context, leading to having stronger perceptual and structural encoding, reflected in the P1 and N170 respectively. In the present study, however, target faces and contextual voices were input from visual and auditory domains, respectively. These two stimuli were not close in space. Attending to one stimulus type will not increase the attention towards the other stimulus type. Moreover, the encoding of voices is thought to be more facilitated than the encoding of faces. The attention may be therefore more accessible to be captured by voices than by faces. Due to emotional salience, angry compared to neutral vocal expression should capture more attention, thus resulting in occupying more attention allocated for target faces. The increased occupation may reduce perceptual and structural encoding of relevant faces. At later time ranges, for example LPP, individuals are able to distribute attentional resources in a controlled way. In previous studies, visually contextual stimuli, negative contextual stimuli in particular, increase motivational values associated with spatially close target faces. These increased motivational values may allow the participants for paying more attentional resources towards relevant faces. In the present study, vocal expression had interfered with the encoding of faces in preceding P1 and N170 time ranges. In order to exclude the interference effects of vocal expression, angry vocal expression in particular, participants may pay large attentional resources to have an elaborate encoding of the faces. Increased attentional allocation may lead to elaborate encoding of faces within negative context in both the previous studies and the present study. The other reason for consistent LPP effects between the previous studies and the present study may be that the LPP time ranges, individuals integrate the emotions between target faces and contextual stimuli, irrespective of the modality of contextual stimuli. The integration may boost negative emotions to emotionally consistent faces, thus resulting in a more elaborate encoding of relevant faces. Contextual effects of vocal expression on face recognition. During the recognition phase, the N170 responses were larger for neutral encoded target faces that had been encoded with angry compared to neutral vocal expressions. Angry compared to neutral vocal expressions led to smaller FN400 and larger LPP responses in later face recognition. These effects were observed not only for neutral encoded faces, but also for angry encoded faces, particularly when facial expression was not changed in the recognition phase. These findings suggest that preceding angry vocal expression influences neural responses in different stages of face recognition. Regarding the N170, it has been shown that recognition related N170 responses were decreased when they had been encoded with distractors than without distractors, suggesting that brains can process the interference effects of previous vocal expression in N170 time ranges during face recognition. Accordingly, the findings in the present study suggest that In the recognition phase or after the encoding phase, neutral faces are generally inferred less by previous angry compared to neutral vocal expressions, as mentioned in section 4.1. Vocal expression interfered with the encoding of neutral faces, particularly at early time ranges of face processing. At later time ranges, however, participants took the initiative to pay large attention or resources to have a complex and cognitive encoding of these neutral faces, in particular within angry vocal expression. This increased attention allocation might have relevant neutral faces being coded very elaborately, even being more elaborate than the neutral faces within neutral vocal expression. Thus, in general, neutral faces were interfered less by previous angry compared vocal expression after the encoding phase. However, the N170 effect is not shown for angry encoded faces. The N170 is sensitive to current threat related information, for example, anger and fear. This sensitivity is suggested to resist the processing of previous information. Therefore, at N170 time ranges in the present study, the brains may have a focus on processing current threat related information associated with angry faces and resist the processing of preceding interferences, effects elicited by vocal expression, leading to the reduction of the effect of vocal expression. In later time ranges, FN400 is an index that reflects stimulus familiarity, with smaller responses to familiar compared to unfamiliar items. Recognition related LPP is thought to be associated with elaborate recollection. The response is larger for learned compared to novel items. Accordingly, the findings in the present study indicate that faces are considered as more familiar and have stronger recollection when the faces were presented with angry compared to neutral vocal expression. As mentioned above, the effect of angry vocal expression may be associated with elaborate encoding at late time ranges of face processing. For angry faces, this effect of angry vocal expression may be also related to emotion integration between angry facial and vocal expressions. It is notable that different from N170, FN400, and LPP are also sensitive to preceding information regarding context emotion. Therefore, in the present study, brains can process preceding context in FN400 and LPP time ranges, even for angry faces, resulting in observing effects of contextual emotion also for relevant faces. However, there were not any effects of vocal expression in the changed condition. When the faces changed into a new expression, retrieval of the faces became much more difficult. Participants may try their best to recognize the faces irrespectively of the emotional content of preceding vocal expression, thus resulting in the reduction of the effect of vocal expression. For a behavioral response, we did not find any effects of vocal expression on face recognition, for example, D line, irrespective of whether the faces showed an unchanged expression or a changed expression. The failure of the effect of vocal expression in the changed condition may be due to high task difficulty. For the unchanged condition, this finding was consistent with Pierre Gaudy and colleagues' 2016 study, which showed similar hit rates for neutral faces within neutral positive and negative pictorial contexts. However, the study by van de Stock and de Gelder 2012 showed reduced hit rates for neutral faces in negative and positive compared to neutral picture and body expression contexts. The differential findings among these studies may be associated with exposure duration in face encoding and recognition. In van de Stock and de Gelder's 2012 study, faces were instructed to be encoded and recognized within a very short time. For example, 1000 milliseconds, whereas exposure duration was much longer in Pirgadi et al. 2016 study and the present study, 3000 milliseconds and 2500 milliseconds respectively. Long exposure duration may be facilitated in retrieving the faces in general, and thus reduce differential recognitions in different emotional contexts. New effects. We also analyzed the old new effects on P1 and 170 FN400 and LPP responses. Consistent with the hypothesis, the results show that there were no old new effects on P1 and N170 responses, similar to previous studies. The recognition related LPP responses were larger for learned as compared to novel faces. However, different from some previous studies, we did not find an old new effect on FN400. Schaefer et al. 2009 showed that ONU effects were reduced for extremely high and low negative stimuli, suggesting inhibition of memory function for these two stimuli. In addition, Ventura-Vort and colleagues in press show that when objects were learned with either emotional or neutral task irrelevant pictures, the ONU effects were reduced in the neutral condition, possibly due to reduced motivational values for the objects in the neutral condition. In the present study, angry vocal expression may increase negative evaluation for emotionally consistent faces. The angry vocal expression may allow neutral faces for being evaluated as slightly negative. In addition, the other half of faces were presented with neutral context. Therefore, reduced ONU FN400 effects may be because target faces are inhibited in memory function in the angry voice condition and have low motivational values in the neutral voice condition. Limitations and future directions. We would like to list some limitations of the present study and suggest outlines for future research. Firstly, the present study found that in time ranges of P1 and N170 during the encoding phase, the responses were smaller for angry compared to neutral voices over parietal occipital scalp sites. However, as is shown in Figure 2, there are also effects of vocal expression over central scalp sites. These effects seem to be associated with auditory rather than visual processing. Therefore, it is still uncertain whether the decreased P1 and N170 responses to faces within angry compared to neutral vocal expression reflect an attenuation of visual ERPs in these time ranges, or an artifact due to auditory ERPs distorting the visual ERPs. Future studies should further investigate this issue in more details. Secondly, while the present study found the effect of vocal expression on face encoding and recognition, only angry and neutral vocal facial expressions were used. It is still uncertain what the effect of vocal expression will be like if other emotional vocal and facial expressions, for example, fearful and happy expressions, are used. It is also uncertain whether the effects of contextual emotion on face encoding and recognition would be like when other auditory stimuli or stimuli of other modalities, for example, olfactory stimuli, are used. Future studies may investigate these issues for more details. Thirdly, it is still unknown why the effect of vocal expression on the LPP were distributed over central parietal scalp sites in the encoding phase, but over central scalp sites in the recognition phase. Future studies may test the generate sources for these two LPP. Finally, we failed to find any other databases regarding vocal expression, which are similar to the database of the Montreal Effective Voices used in the present study. In addition, we now have not got enough knowledge and experience to create a new database regarding vocal expression. Therefore, in the present study, the number of voice stimuli was much smaller than the number of facial stimuli during the encoding phase. The unequal number of these two expressions might influence the effect of contextual emotion. Conclusion. The present study found that during the encoding phase, P1 and N170 responses were smaller for both angry and neutral faces. When the faces were presented concomitant with angry compared to neutral vocal expressions, for angry faces, however, LPP responses were larger in the angry voice condition than in the neutral voice condition. In a later recognition phase, the N170 responses were larger for neutral encoded faces when they had been encoded with angry compared to neutral vocal expressions. Previous angry compared to neutral vocal expressions led to smaller FN400 but larger LPP responses. And these effects were observed not only for neutral encoded faces, but also for angry encoded faces, particularly when facial expression was not changed in recognition phase. Therefore, the present study indicates that contextual emotion regarding vocal expression affects neural responses during face encoding and recognition.